Are you preparing for a data science, machine learning, or AI interview? Well, listen up, because today we are tackling the absolute top interview questions that recruiters are asking right now. Stick around until the very end, because we're taking some dense technical concepts and turning them into the ultimate mock interview prep session. This explainer is basically your cheat code to landing that job. So, what is the number one most asked topic in modern AI interviews? It's the transformer architecture. Literally every single major large language model today, we're talking GPT, BERT, T5, they are completely built on transformers. You absolutely cannot walk into an AI interview right now without knowing exactly how these models work under the hood. It's your golden ticket. Here's our quick study guide for today's explainer. First, we'll cover overcoming seek-to-seek limits. Then, self-attention. Third, positional encodings. Fourth, attention math. And finally, we've got a bonus rapid-fire round to really help you stand out to any hiring manager. All right, let's jump straight into Section 1, Overcoming Seek-to-Seek Limits. Okay, picture this. The interviewer leans in and asks, how do transformers overcome the challenges of traditional seek-to-seek models like RNNs and LSTMs? Now, a lot of candidates mess this up by jumping straight into the complex math, but you've got to explain the history and the why first. You say, traditional RNNs process text sequentially. They literally read one word, and then the next word, and so on. It is incredibly slow. Plus, for longer sentences, they suffer from this fixed-length bottleneck, basically squishing a whole paragraph into one tiny vector. Transformers, on the other hand, they process all tokens in parallel, all at the exact same time. They replace that slow sequential reading with something called self-attention, which completely eliminates that bottleneck. When you answer this, you definitely want to drop these exact key phrases to look like a total pro. Highlight that transformers win because they replace recurrence with self-attention. Mention that this enables massive parallelization, eliminates those fixed-length bottlenecks, easily learns long-range dependencies, and keeps gradients stable. That last part, stable gradients, interviewers absolutely love hearing that. Moving right along to Section 2, the self-attention mechanism. This is a big one. They'll ask, can you explain what attention is? This is your moment to prove you truly grasp how an AI understands context and meaning, rather than just memorizing vocabulary. Essentially, attention is a mechanism that tells the model which specific words it should focus on when processing a particular token. Think about this sentence. The cat that chased the mouse was hungry. When the AI is processing the word was, self-attention allows it to directly connect was to the word cat, not the mouse, even though mouse is right next to it. It dynamically assigns mathematical weights to the most relevant parts of the entire sentence. And here is how you break down the actual algorithm step by step, so it's super easy to recite under pressure. Step 1. For every token, we create 3 distinct vectors: a query, a key, and a value. You can think of the query as the word asking a question and the key as the label it's checking against to find an answer. Step 2, we compute similarity scores by comparing the current word's query with all the other keys. Step 3, we apply a softmax function to turn those scores into probability weights. And step 4, we just multiply those weights by the value vectors. Boom! That's your final output. It's a beautifully logical flow. Okay, let's pivot to Section 3, positional encodings. This is a tricky follow-up that senior engineers love to test you with. Since transformers process everything in parallel, how do they actually understand word order? A common trap here is forgetting that without sequential reading, sentences like "the dog bit the man" and "the man bit the dog" look completely identical to the AI. To fix this, we literally have to inject an order tag right into the word's embedding. We call these positional encodings. They're simply numerical representations added directly to the token vectors before they ever enter the transformer network. By combining the word vector and this position vector, we feed the model both the meaning of the word and its exact spot in the sentence all at once. And here's a pro tip for massive bonus points. Mention the different types of encodings. Tell them the original transformer paper used absolute positional encodings based on fixed sine and cosine functions. It sounds super impressive. But also add that modern models often use learned embeddings that optimize during training or relative encodings that just focus on the distance between the tokens. All right, time for the make or break part of the interview. Section 4, deep dive into attention math. Imagine the interviewer hands you a marker and says, how exactly are attention scores computed, and what is the role of the dot product? Do not panic. The math is actually totally approachable once you break it down visually. Just write out the scaled dot product formula. Attention equals the softmax of Q times K transpose divided by the square root of dk, all multiplied by V. The absolute key here is explaining that division part, the scaling factor. Tell the recruiter we scale the dot product scores down because in really high dimensions, these values get massive, which totally destabilizes training. Scaling keeps the gradient smooth, predictable, and stable. And as for what the dot product is actually doing, it's just measuring similarity. If the query vector of one word and the key vector of another word point in the exact same direction, their dot product is a large positive number. The model is literally just using math to find a perfect match between related words. It's like a giant puzzle seamlessly coming together. Awesome job so far. Now let's crank up the energy for Section 5, the bonus rapid fire round. We've got to be fast and punchy here. Rapid fire question 1. What is multi-head attention? Multi-head attention simply means performing multiple attention operations in parallel. Think of it like having multiple little experts inside the model, looking at the exact same sentence at the same time. One expert head is checking for subject-verb agreement. Another is checking for long-distance context. Another is looking at syntax. It captures all these rich, different relationships simultaneously. Next, rapid-fire question 2. Why do we use the softmax function? Softmax is crucial because it basically takes messy, raw dot product scores and converts them into perfect, clean probabilities that all add up to 1. It turns raw math into a clean percentage that the AI can easily understand, highlighting the important words, pushing down the irrelevant ones, and making the whole training process smooth and differentiable. And there you have it. You are absolutely ready to walk in and ace that interview. You now understand the core mechanics of the single most important architecture in modern AI. But let me leave you with one final thought. Transformers completely revolutionized the world, right? But they're incredibly compute hungry. Do you think the Transformer will remain the absolute king of AI for the next decade? Or is a brand new, highly efficient architecture just waiting to be discovered? Let me know your thoughts in the comments below. And hey, if this explainer helps you prep, make sure to hit like, subscribe, and comment what AI topic we should cover next. Go get that job, and I'll see you next time.